Good morning. I'm going to give people a minute to join. Hopefully it's more than just me and you.
Are we doing properties chapter 26 today?
I finished chapter 26. We're going to start chapter 27 on color.
Okay.
But I'm going to start off with a brief little recap of chapter 26. So we're going to start in just about 1 minute. Audio on, bam. Pen working. Okay, well, while people are still joining, let me do a little quick recap of chapter 26. Just so you know, I sent out an email. We're only going to cover 2 more chapters this semester. Well, this semester being 2 weeks. Today, I'm going to cover chapter 27, finish it up on Thursday, and then the last week, we're going to cover chapter 28. So let me do a quick little just recap. So if you remember, light, all forms of light are just an electromagnetic wave. And I have a cool little animation to show you. Share, let's go here. So remember, surrounding every stationary electron is an electric field. And if that electron is also moving, not only is there an electric field around it, but there's also a magnetic field. Well, if the charge is oscillating up and down, then what ends up happening is that creates an oscillating electric field. And one of the things Einstein discovered is that an oscillating electric field creates an oscillating magnetic field. And an oscillating magnetic field creates an oscillating electric field. So all light is produced by a charged object, usually an electron, which is oscillating up and down at some frequency. The frequency that it oscillates up and down at is going to be the same as the frequency of light that it produces. So let me stop that for a second. Do a new share. Ba-ba-boo. Okay, in terms of light, visible light is no different than radio waves or microwaves or infrared. The electromagnetic spectrum consists of light of all frequencies. We just happen to be sensitive to a very, very narrow range, but there really is no difference between a microwave, visible light, ultraviolet, X-rays. They're just different frequencies and different wavelengths. So one of the things we're talking about is how does light get through a transparent material? So a transparent material is something like glass or water that you can see through. And light always travels at the same speed in a vacuum. Speed of light, 186,000 miles per second. But in order to travel through the atmosphere or through glass or through water, the way it does that is the light comes in and then it gets absorbed by the first atom in the transparent material. Let's just say it's glass. That light completely disappears. An electron in an atom in the glass absorbs the light, causes the electron in the atom to oscillate up and down, and then it passes on new light. That new piece of light is completely identical in every way, but technically it's a new piece of light. The old light was absorbed, no longer exists. The energy got absorbed by the atom, and then that atom passed on the light, the energy, to the next atom, to the next atom, and so on and so forth. That's just sort of a quick little recap of chapter 26. So the way light gets through a transparent material is by getting absorbed and re-emitted constantly until it passes through the material. Now, it's also possible for the material to absorb the light without re-emitting it. And that happens if the frequency of the light matches one of the natural frequencies of the glass or the water or whatever it's passing through. If that happens, a resonance phenomenon occurs. So if the frequency of the light matches the natural frequency, let's say of the glass, what that does, once the atom absorbs the light, instead of oscillating a little bit and then passing it on, it oscillates a tremendous amount. It runs into neighboring atoms and it loses that energy as heat rather than passing it on as another piece of light. So let me just pause there. Are there any questions that I can answer about chapter 26 before we move on to chapter 27? Going once, going twice. off with the recap. On with the hat that I had lost yesterday. I was very upset, but I found it. Okay, so let's start chapter 27. Okay, so a couple things we're going to learn in chapter 27. It's all about color. Why do things appear to be the color that they are? And let me just give you a little preview. If something appears red, and for now we're talking about an opaque object, one that you can't see through. So like this shirt. Why is this shirt red? The big picture is I have white light shining on my shirt. White light consists of light of all frequencies mixed together. This shirt happens to be absorbing most of the frequencies of light except red. Red is what gets reflected back to you, and that's the color that you see is the color that gets reflected by an opaque object. We call that selective reflection. And it basically means that objects are going to selectively reflect specific colors of light, and that's the color of the object that you see. We'll also talk about selective transmission, and that's for an object like a pane of glass that you can, or a filter, that will only let certain frequencies of light pass through it. And then we're going to talk about mixing colored lights. So, very interesting, if you ever look at your computer monitor using a really good magnifying glass, what you would see is your computer monitor consists of billions and billions of little pixels. All they are red, green, and blue pixels, and just by adding different amounts of red, green, and blue, you can produce any other color that you could possibly imagine. A lot of times I don't cover mixing colored pigments, but I think I am going to cover that just conceptually because it is kind of interesting. And that's probably what I will do today. And then on Thursday, I'm going to talk about a couple cool things. One, why is the sky blue? A little hint, it has to do only with what our atmosphere is composed of. Mostly nitrogen, and nitrogen tends to scatter blue light better than any other color. We'll talk about why sunsets are red. Same reason, it has to do with what's in our atmosphere. And finally, we'll talk about why clouds are white. Okay, so let's first talk about selective transmission and reflection. We'll deal with selective reflection first. So let's say I've got this little beam of light coming in, and it's hitting some surface. You know, this could be glass, this could be water, let's just say it's glass. Whenever light strikes an object, and in fact, whenever any wave strikes an object, sound wave, light wave, and so on, there's three possibilities for what can happen. So one, I can have the light which is absorbed. If the light is absorbed, light has energy. The object that absorbs the light will heat up a bit, which means this shirt is actually at a different temperature than it would be if it was completely dark out, because this shirt is absorbing some frequencies of light. It's reflecting reddish, back to you. So the fact that it absorbed other frequencies of light means it did absorb the energy that that light had, so it heated up. Two, the object can get transmitted. Not the object, the light. And then three, that object can get, or that light can get reflected. Now, when is it going to get absorbed and when is it going to get transmitted or reflected? Well, remember, if the frequency of light matches the object's natural frequency, then when that atom absorbs that first piece of light, it starts to oscillate wildly because of resonance, and it loses the energy as heat. So if light matches one of the natural frequencies of the transparent object, that object will absorb the light without re-emitting it. If, however, the light has a frequency above or below the natural frequency, then that light is going to get absorbed and then re-emitted. And we've already looked at how light gets through a transparent material like glass. So again, if this was one atom, let's change colors here. Let's do blue. If this was the very first atom that this light runs into, what I would see is that light would that atom would completely absorb the light. It's gone from the universe, and then it's going to re-emit the light, which would then pass to the next atom, which would then get absorbed by that atom, re-emitted, blah, 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 until it eventually gets all the way through. So it's just this constant process of getting absorbed, re-emitted, absorbed, re-emitted, and so on. Now, that's if the object is transparent. The re-emitted light, in essence, is emitted in the same direction that it was traveling to begin with. So that's what happens with a transparent object. Now, if the object is not transparent, so one, an opaque object, this is just one that you can't see through. And what happens with an opaque object is, so let's say in this case, this is, I don't know, it's just a general opaque object. And I've got a beam of light coming in. What happens in this case is it gets absorbed by, let's say, the first atom in this opaque object. And then when it gets re-emitted, rather than get re-emitted in the same direction it was traveling so that it eventually passes through the material, it gets re-emitted in the opposite direction that it was coming. This is just what reflection is I have an object which absorbs light and then re-emits it, but when it's re-emitted, it's not re-emitted in the same direction, it's re-emitted back in the opposite direction, and that's really what reflection is. So if it's transmitted through, it gets absorbed and then re-emitted in the same direction it was traveling until it eventually gets through the material. If it's opaque, so I can't see through it, when that first atom absorbs the light and re-emits it, it re-emits it back in the opposite direction, so it's coming back towards the observer. So let me just pause there before moving on, because that's sort of an important point. So light hits a material, three possibilities. That light can get absorbed, that light can get transmitted through, that light can get reflected. Whether it's absorbed or transmitted through or reflected depends upon how the frequency of the light matches the natural frequency of the material. If it matches a natural frequency, then that light will get absorbed and not re-emitted. The energy that got absorbed will turn into heat. If the light doesn't match one of the natural frequencies, then it depends on whether it's transparent or opaque. The object will absorb the light and then re-emit it. If it's transparent, it'll keep going in the same direction until it gets through the material. If it's reflected, it'll be transmitted back in the opposite direction from which it came. So let me just pause there, open it up. Any questions on that basic concept? Going once, going twice. Sold. Okay, back to OneNote. Now, what's the difference between red and yellow and green and a microwave and an infrared and ultraviolet? It's simply just different frequencies, different wavelengths. Remember, for light, big equation is wavelength of light times the frequency of light equals the wave speed, which for light we write as c. Bigger wavelengths mean smaller frequencies. Smaller frequencies mean bigger wavelengths, but the different colors that we see simply correspond to different frequencies of light. So if I could go back real quick to this charge, which is oscillating up and down. You don't need to know the specific frequencies of red light or violet or things like that. But if I just cause this thing to oscillate faster, I'm going to create an electromagnetic wave with a higher frequency. That's the only real difference between something like this oscillating up and down very rapidly or oscillating up and down slower. The frequency that it oscillates up and down at is the frequency of the electromagnetic wave that it produces, and light just happens to be a very narrow range of frequencies that our eyes have evolved to be most sensitive to over the years. Okay, so let's go back to that again. So kind of going through this last chapter a bit, but our sort of visible spectrum, the sort of acronym that we tend to use is Roy G. BIV. For red, orange, yellow, and these are all considered low frequency light. Green is sort of considered mid-frequency. And blue, indigo, and violet are all considered high frequency light. So our Roy G. Biv is sort of the acronym we use to remember the colors in the order. Red, orange, yellow, lower frequencies. Green, sort of mid-frequency. Blue, indigo, and violet, high frequency. And again, if we really wanted to, do I have the frequencies here? So sort of here's the electromagnetic spectrum again. If you wanted to know the frequency of red light, can I draw on this? Let's shift F5. The frequency of red light is 4 times 10 to the 14 hertz. Frequency of violet light is about 8 times 10 to the 14 hertz. 10 to the 14, trillion is 10 to the 12. So 10 to the 14 is 100 trillion times. So if you had a charged object or an electron, and you could oscillate it up and down 100 trillion times a second, you would produce visible light. If you oscillated it up and down more frequently, then you would produce ultraviolet light. Even more frequently than that, X-rays and gamma rays have the highest frequency, smallest wavelength. Okay, let's get rid of this for a second. Stop share, go back to OneNote. Okay, so there is a specific frequency for every single color, except white and except black. It ends up, like I showed you, red has a frequency around 4 times 10 to the 14 hertz. Violet has a frequency around 8 times 10 to the 14 hertz. There is no frequency of white light. There is no frequency of black light. So white is a mixture of all colors, and black is the absence of color. So real quick, going back to this animation real quick. If you could see, let's say, 2 different visible light waves, one that was oscillating at a frequency of 4 times 10 to the 14 hertz and one that was oscillating at 8 times 10 to the 14 hertz. There is no difference between the electromagnetic waves, how they are behaving. It's just they're oscillating at different frequencies. And what we're going to see this chapter is it's really how our brain perceives these different frequency electromagnetic waves. Kind of mentioned before, we have these things called cones in our eyes that are sensitive to color. And depending upon how our cones are activated, we interpret the electromagnetic waves as different colors. All right, so going back. White, there's no frequency of white light. Black, there's no frequency of black light. So when light of all frequencies is hitting our eyes, then we see that as white. When there's nothing from a particular region hitting our eyes, we interpret that as black. So all colors combined together, we see as white. Nothing, no light at all coming from a particular area, we see as black. Okay, so keeping in mind that an opaque object doesn't let light pass through it. What ends up happening then is all opaque objects absorb some frequencies of light and then they reflect the rest. Well, the color of an object is simply the color of light that it reflects. So very important concept, the color of an opaque object is the frequency of light that it reflects. So if you see something as purple or violet, frequency of violet's about 8 times 10 to the 14 hertz. What that means is, let's say white light is coming in. I've got an object which is going to absorb most of the frequencies of light except violet. It will then absorb violet and then pass it back the direction it came. It'll reflect it. The fact that we see this certain frequency of light coming from the object, that's the frequency of the light that we're going to detect from the object. So if it's reflecting violet light back, that's what we will see. So an object is red because it reflects red light back and it absorbs the other frequencies to us. Okay, let's actually pause for a clicker question. And just so you know, had some questions just about the grades that I sent out. I'm not doing anything with class participation in terms of the clicker questions that I'm doing during these Zoom presentations. I know only about a third of the class is watching it live. So can I do a poll here? Poll. So the question is this, question 27.1. An object that reflects light of all frequencies always appears white. True or false? And actually I have a true or false one. Yes or no? Let's do true. So I launched a poll. I'm not sure if you all can see it, but just a simple clicker question. An object that reflects light of all frequencies always appears white. Is that true or false? Take a moment, see if you can, on your computer screen, you should see a poll. It's completely anonymous. If you're on your phone, you might not be able to see it. But the question is, true or false? An object that reflects light of all frequencies always appears white. What do you think? I give you 30 seconds. All right, we've got true edging up. Oh, now it's even. We've got 50% say true, 50% say false. We got one other person want to do a tiebreaker. Going once, going twice. Up, and we're going to end the polling. Let's share the results. We have out of 9 people, 56% of you say A, true, 44% say B, false. Drum roll, please. The answer is false. Why? In order for something to appear white, it has to have all frequencies of light that it can reflect. Let's say I have a white piece of paper and I only shine red light on it. If I only shine red light on it, then it can only reflect red light. So what is the color of an object that reflects light of all frequencies? The answer is it's going to be whatever color light is shining on it. So if I have something that reflects light of all frequencies and I only shine blue light on it, it's going to appear blue. If I have something that reflects light of all frequencies and I only shine red light on it, it's going to appear red. So the correct answer here is, if an object reflects light of all frequencies, it is going to be the same as the color of light that shines on it. Don't read that last part yet. So actually I had one more clicker question I should have asked before I showed you that. Let's do a second one. So one, if something reflects light of all frequencies, it will be exactly the same as the color of light that is being shined upon it. If I'm shining white light on it, then it can reflect all the frequencies that are contained within the white light, so it'll appear white. But if I only shine yellow light on it, it cannot appear white because it only has yellow to reflect. Okay, another poll, relaunch polling. Continue. Second poll for this one is 27.2. For this one, the question is, what happened here? 1 second. Okay, 27.2. Now we're looking at not an object that reflects light of all frequencies, but an object that absorbs light of all frequencies. So 27.2, an object that absorbs light of all frequencies always appears black. True or false? What do you think? An object that absorbs light of all frequencies always appears black. All right, we've got, 50-50, 50-50. Oh, B's slightly ahead. B is slightly, B is running ahead. B is pulling ahead. We've got 5 out of 7 say B, false. All right, wait for one other person if you want to go. Going once, going twice. Let's end this poll. Share the results. The results are 67% of the people say false. In this case, the answer is true. If something absorbs light of all frequencies, then it doesn't matter what frequency of light I shine on it, it's going to absorb it. And if something doesn't reflect light of any frequency, it will always appear black. Right? The color of an object is the same as the color of light that it reflects. Something that's white reflects all frequencies of light, but it can only appear white if I'm shining white light on it. Now, something that absorbs light of all frequencies is always going to appear black, because no matter what frequency I shine on it, it will absorb that, not reflect it. And when we don't see any light coming from this object, we interpret that as black. Okay. Let me pause for a second and just open it up to questions about that particular concept. So white is a mixture of all frequencies. If something's going to appear white, it has to reflect all the frequencies to us so we see them all at the same time. Something that's black absorbs light of all frequencies, and when we don't see any light coming from a particular object, we interpret that as black. So if something absorbs light of all frequencies, any light I shine on it is going to get absorbed. Nothing's going to get reflected back. I'm going to see that object as black. If something absorbs or reflects light of all frequencies, it will be whatever color I will shine on it in terms of light. So if I shine only red light on, let's say, a white piece of paper, that white piece of paper will reflect the red light. I'll see it as red. If I only shine blue light on it, it only has blue light to reflect. I'll see it as blue. But if I shine light of all frequencies on it, then it can reflect all of that. We would see it then as white. Questions on that before I move on? Okay, moving on. What am I going to? OneNote. Okay, so going back to that, object that reflects light of all visible frequencies is the same as the color of light that shines on it. An object that absorbs light of all frequencies is always going to appear black. Now, one other thing I want to mention is we don't notice this very much because we're pretty much always surrounded by forms of white light. Our sun is emitting light of all frequencies. Any light bulbs that we have are generally white light bulbs. They are emitting light of all frequencies, which means that there's always frequencies of light in terms of colors that an object can reflect back. So this object, again, is red because I have white light shining on it. My shirt is absorbing all the frequencies of light except for reddish orange. That's what's reflecting back. But here's the thing. What would happen if I only shined blue light on it? In order for something to appear red, it has to have red light to reflect back. So technically, the color of an object depends on the kind of light that's illuminating it. Meaning, an object can only reflect frequencies of light that are present. I can't reflect red light if there's no red light shining on it. What this means is, come on, an object can only appear red if there's red light present to reflect. And so I can, like for stages and for performances and for plays, you can actually change the color that something appears by changing the color of light that shines on it. So let me stop the, oh no. So under animations, our physics lab tech, John, created this really great little YouTube video that you can link to here. And there's all of these great little animations. And I just want to show you a couple in terms of light. So let me stop this, do a new share, screen share, and I want animations, PowerPoint radiating charge. And for this, we want stage lighting. Object, okay, so let's, actor appears black. Okay, tapped color, oh, so, oh, cool. So let's say I've got a red object. If I shine red light on it, it will obviously appear red. If I shine white light on it, it will appear red because it then has red light to reflect. But let's say I were to, and here, like the person's arms are black. Why is that? Because it's absorbing all frequencies of light. The eyes are white. Why? Because they're reflecting all frequencies of light. And the little stem here, or the leaf, is green because it reflects green light. Now I'm shining white light on it, so there's all frequencies present. But let's say I shine blue light on it. The apple is going to appear black because I'm shining blue light on something that only reflects red light. So I shine blue light on it, it's going to absorb that blue light. No light is getting reflected, so it's going to appear black. If I shine green light on it, there is no red light for it to reflect, so it's going to appear black. So I'm going to do more on that later, but the point is that the color of an opaque object is the same as the color of light it reflects. But if it doesn't have that light to reflect, I'm not going to see a red object as red unless it has red light to reflect. So in terms of selective reflection, like I said, the color of an opaque object is the color of light it reflects. So a red object is red because it reflects red light. A blue object is blue because it reflects blue light. But if I shine red light on a blue object, it's going to absorb that red light. It's not going to reflect anything, so it will not appear blue. In that case, it would appear black. Now, there's a difference between an opaque object and a transparent object. So a transparent object might be just like a filter, a red filter. So for a transparent object, it is only transmitting certain colors of light. So for example, a piece of blue glass, transparent object is only letting certain colors pass through it, and it's absorbing the others. An opaque object is only reflecting certain frequencies of light. A transparent object is only letting certain frequencies pass through it. So I don't have any blue filters or blue pieces of glass, but if I had a blue filter, I would appear blue. And the reason is because white light would be hitting the filter would only let blue light pass through it, and so you're only going to see blue light passing through the filter, it would appear blue. And again, I wish I had some of these cool demos to show you, but I don't have anything with me. Let me pause. Any questions about that particular concept? So selective reflection means an opaque object is only going to reflect certain frequencies. The color of an opaque object is the color of the frequency of light that it reflects. Question, Allison? Anybody? Going once? Going twice? Okay. So let me quickly go to PowerPoint. And a question I have for you, I didn't really ask it, but if I took a white piece of paper outside in the sun, what color would the white piece of paper appear? And the answer is, it would appear to be white. And that tells us that the sun is emitting light of all frequencies. If the sun didn't have all frequencies of light being emitted, and I had a white sheet of paper, it would not appear white unless it could reflect all frequencies back. So the sun emits light of all frequencies, right? Not just visible. The sun is emitting ultraviolet, the whole spectrum. But this plot just shows the different frequencies. So like here's my low frequency, red, orange, yellow. Here's my middle frequency, greenish. My high frequencies, blue, indigo, and violet. what I would see if I looked at how much light is being emitted at every certain frequency, our sun is emitting more light in the yellow-green part of the spectrum than any other part. So here's, how much light is being emitted on the axis here. The higher up this is, the more light that's being emitted. So the sun is emitting most of its light in the yellow-green part of the spectrum. And over the years, our eyes have evolved to be most sensitive in that range of frequencies. So you may not have known this, but we see better in the yellow-green part of the spectrum than any other color. So our eyes over the years, since that's where the sun is emitting most of the light, over many millions of years of evolution, we've evolved to be most sensitive to where the sun is emitting most of its light. Now what happens is, I mentioned that our eyes have these sort of light detectors. And if you remember, we had two different kinds. We had cones, which is how we see color. And we have rods, which are very sensitive to lightness and darkness and motion. What I didn't mention, or maybe I did in chapter 26, but we actually have 3 different kinds of cones. Now, some animals have many more different kinds of cones. What was it, the mantis shrimp? One of them has something like 10 or 15 different kinds of cones, so they have much better color vision than we do. But we, if you look in our eye, remember on the back of our eye called the retina, we have sort of these light antennae that detect light. Rods are responsible for us seeing color. I'm sorry, cones are responsible for us seeing color. Rods are responsible for us seeing lightness and darkness and motion. Well, our cones are actually separated into 3 different kinds. I have cones that are sensitive to low frequencies of light, so red, orange, yellow. I have cones that are sensitive to medium frequencies of light, and I have cones that are sensitive to high frequencies of light. And what ends up happening is if all 3 types of our cones are stimulated equally, we perceive white light. So I know this class is not very mathematical, but we're going to do a little bit of color math. Whoop, 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 color math. So our very first equation. So I just talked about this. Sun's emitting light of all frequencies, kind of like what I just did on the PowerPoint, but it's brightest in the yellow-green part of the spectrum. It's emitting more light in the yellow-green part than any other part. We've evolved to be most sensitive to that part of the sun spectrum. So just to throw this out, you have a question in your homework. And just a quick little story, you may not remember this, but I think it was like 15 years ago, they changed the color of fire engines and fire trucks. Most people know fire trucks are bright red. And at one point, about 15 years ago, they changed the color to this really pukey orange or yellow green, because the thinking was that's where our eyes are most sensitive. People will be more likely to see the fire truck if it's this color that our eyes are most sensitive to. But after they changed the colors of the fire trucks, it failed tremendously. And the reason is, it's just, what's the word? I'm losing the word, but basically habit. Anyway, we over the years have just come to associate fire trucks with the color red. And so you hear a siren and people were automatically looking for a red fire truck, and a yellow-green fire truck was not even on their radar. So even though we see yellow-green better, we're so used to looking for a red fire truck when we hear a siren that people were missing the fire trucks. So anyway, the question, one of your homeworks is, why are common tennis balls the color that they are? And the reason is simply because that's the color of light that our eyes are most sensitive to. And if you ever watched Wimbledon or a tennis match, some of these professional tennis players can serve at 120, 130 miles an hour. You only have a split second to react to a serve and get your body in the right position to return it. And if you're going to react that quickly, you have to be able to pick up the ball very, very rapidly. And so the color of a tennis ball is the color it is because that's where our eyes are most sensitive. Okay, so our eyes have three different kinds of color sensors called cones. And like I said before, they're sensitive to low, which is red, orange, yellow. They're sensitive to medium, which is green, and sensitive to high frequencies, blue, indigo, and violet. When all three types of our cones are stimulated equally, meaning white light comes in, white light consists of light of all frequencies. The low frequency light will stimulate the low frequency cones. The middle frequency light will stimulate the middle frequency cones, and the high frequency light will stimulate the high frequency cones. When all three types are stimulated equally, that's when we see white. So in terms of color math, your very first color equation is this: red plus green plus blue equals white. So this is if I have equal amounts of red, green, and blue mixed together equals white. So red plus green plus blue equals white. And the other thing is, since we only have three kinds of cones that are sensitive to low frequencies, reds, mid frequencies, green, high frequencies, blue, I can take different amounts of red, green, and blue and add them together to produce any other color. I forget exactly how many colors a computer monitor can produce. Millions. Those millions of colors are all the result of three little pixels, red, green, and blue, added together with varying amounts of red and green and blue. So we call red, green, and blue the additive primary colors of light. So I can add red, green, and blue in any combination to produce any other possible color. So let me go back to these animations. So one, which one should we look at? Just in terms of mixing color. So color mixing game. This was actually written by our lab tech, John. Let me share that real quick. Staging, lighting. Not that one sec. Color mixer. And let's set this circle to background color. Okay, so one, if I have all three pixels being stimulated equally, let's circle to background color. Oh. So hi, show answer, set circle to background color. Okay, so let's not worry about this. This color game is you're trying to match the outside color. So like here, you try and see how much red, how much green, and how much blue I would need to add together to produce this particular one. Oh, and this shows you the answer. Set circle to background color. So if you've ever done any programming in HTML, you can set the color of your font or the color of something by setting different amounts of red plus green plus blue. So in this case, the background, this purple color, is a combination of a bunch of red, hardly any green, and a bunch of blue. You don't need to know the exact numbers, but when all three colors are stimulated equally, oh, hide this magnifier. Nope, reset. So let's just look at this middle one. When all three colors are stimulated equally, that's when we as humans perceive white. So if you have a good magnifying glass, many people don't, but if you had a really good one, it's pretty cool to look at a computer monitor. And what you would see is if I was looking at this part of the monitor with a really good magnifying glass, what appears red is really just these teeny, teeny, tiny things called pixels that are just three different kinds: red pixels, blue pixels, and green pixels. And by adding them up in different amounts, you can produce any other possible color. So I could change the amount of red, the amount of blue, the amount of green. And so this is showing you what the pixels would look like. So if I had 142 for red, 184 for green, 62 for blue, it would produce this pukey looking green color. But this is what I would see from far away. But if I had a magnifying glass and I looked at it, what I would see, not this pukey green color, but 3 different pixels, red, green, and blue, just lit up in different amounts. So the very first color equation is red plus green plus blue in equal amounts equals white. Other color equations, and let's just do this. Okay. So you may have studied color mixing as a kid. And let me just throw this out here now. There's a difference between mixing colored lights and mixing colored pigments. And what I'm going to talk about now is just mixing colored lights. So we saw red plus green plus blue together equals white. So the first one is, what is red plus green equal? Anybody know? Red plus green. If I add red plus green, what I get is yellow. So like real quick, what's happening here? These pixels are all red pixels. These pixels here are all just green pixels, but right here, I have both red pixels and green pixels lit up. When my brain sees equal amounts of red and equal amounts of green, it interprets it as yellow. So I'll write this down once I show all of these different combinations, but red plus green equals yellow in terms of light. Red plus blue equals magenta. So if I take equal amounts of red and equal amounts of blue, I get magenta. If I take equal amounts of blue, sorry, I had a sneeze. All right, equal amounts of blue plus equal amounts of green equals cyan. And then if I add all 3 together, kind of a cool little picture here. So red plus green is yellow, where they overlap. Red plus blue is magenta, where the red and blue overlap. Blue plus green is cyan, and where all 3 overlap is white. So let me stop this and just go back to my lecture notes. So in terms of color math, we have 4 main equations. First one was red plus green plus blue equals white if I add equal amounts. The other 3 are over here. And if this was done live, I'd kind of show you, we have these really great spotlights I could show on the whiteboard, and you would see exactly what I showed, is that when I add red plus blue, I get magenta. When I add red plus green, I get yellow. And when I add blue plus green, I get cyan. So sharing these simulations one more time. Let's go to a different one. Tracking. That's not doing it. Interactive. Okay. Well, anyway, going back here. So let's just focus on this middle part. The game is trying to match the outside color by adding different amounts of red plus green plus blue. But just focusing on this middle circle, red plus green together, equal amounts gives me yellow. Only equal amounts of red and green. If I have less green, it's no longer yellow, it's a different color. But what I would see is, if I looked close up at a computer monitor, the red pixels and the green pixels have the exact same intensity. They're emitting the same amount of light. There's nothing coming from the blue pixels. So equal amounts of red plus equal amounts of green is blue. Equal amounts of red plus equal amounts of blue is magenta. And again, what I would see in a computer monitor, the red pixels and the blue pixels are emitting the same amount of light. Nothing is coming from the green pixels. And then red or green plus blue is cyan. And then again, if I add all 3 together, I get white. So here, just as a guess, what do you think, what combination would produce this light blue color? And I have no idea. Let's share the answer. So this light blue color is produced, and let's see if we can do it, by mostly blue with a little middle bit of green, and then hardly any red. You can see I don't have it exactly. I don't know if you can see it, but I can still see it. But these are the exact numbers that you would need to use to get that particular color. It's a really cool concept, right? Our computer monitor can produce millions of different colors, countless shades of red, countless shades of blue. But all it is red, green, and blue pixels added together in varying amounts. Ha! Booyah! Okay, I spent a little bit longer on everything than I wanted, but feel like I gave you a great little introduction. On Thursday, I'll talk a little bit more about color math, and then we'll talk about why the sky is blue, why sunsets are red, and why clouds are white. So I'm going to just open it up for questions about this for a minute or two. And if there's no questions, sort of end office hours, end lecture, bring in office hours. Any quick questions I can answer about anything I cover from chapter 27? Nope. If not, I'm going to take out Physics 10 lecture. Bring in Physics 10 office hours. Thank you for everybody that joined me live for the lecture. Thank you, Jamie. Thank you, everybody. I'll stick around until about 10:45 if people have questions. If not, have a wonderful day. I will get this posted to YouTube as soon as I can. Thank you, everybody. Have a wonderful day. Let me know if you have any questions. And
Hi, I have a question.
What's up, Allie?
Oh. I might be jumping ahead a little. I'm trying not to, but on the homework assignment, so question 4 asks about the inkjet printers.
Yes.
And then question 5 has some of those equations. So for the inkjet printer, it's using color subtraction, right?
It is. So like for a magazine, for anything that you print, it's not emitting its own light. So we call it color subtraction because what's happening is you've got white light hitting, they're called pigments. And a pigment is just like a dye. It's something that's designed to absorb specific frequencies of light. And so it ends up that if you like go and buy ink for your printer, you're not buying red, green, and blue ink. You're buying yellow, you're buying magenta, you're buying cyan, and you're buying black. And they work not by emitting light, but they work by absorbing specific frequencies of light. So just real quick to follow that up, actually let me just share something with you. Let's do this PowerPoint. So here's the whole thing with adding primary colors. And this is if I'm adding colors of light. But pixels, where is that? Work differently because they are designed to absorb specific frequencies. So like here, you can kind of see that if I were to take yellow, not light, but a yellow pigment and mix it with a magenta pigment, it would produce red. And they're called subtractive primary colors because light is shining on it and they're subtracting off most of the light and only reflecting specific portions of it.
Okay.
So just so you know, I'm not going to ask you to know any sort of rules of color subtraction. I'm going to mention this just because people get confused. Well, why aren't the ink that I buy red, green, and blue? And that's because there's a difference between mixing light and then mixing colored pigments. And like if you've ever tried drawing with crayons, if I take a red crayon and a green crayon, I'm not going to produce yellow light or yellow color. So there's a difference between adding light and adding pigments together. So the one thing, go ahead.
Adding pigments uses color. It uses color subtraction because you're just subtracting light. You're not adding it.
Right. So the only way I could do color addition is if I have a bunch of different colors of light and I'm adding them all together. But when I'm shining light, let's say on a magazine, I've got light hitting the magazine. Some of that light is getting absorbed and only some of it is getting reflected. So the way that you control what color a magazine is by subtracting off specific frequencies of light that get absorbed by the pigments. And so you don't need to know the rules of color.
Gotcha.
You don't need to know the rules of color subtraction, but know that when I'm looking at a magazine, so instead of like looking at a computer monitor with a really good magnifying glass, if you looked at a magazine with a really good magnifying glass, which you would see is billions of teeny tiny dots, and those dots would be magenta, yellow, and cyan.
And black? Or no, just
And black,
magenta,
I'm
yellow,
sorry.
and cyan.
Yeah, you
Okay.
could do it without black, but black we use often because then if I didn't have black, I'd need to use more magenta and cyan and yellow to produce black. And in fact, most good printers have two different kinds of black, one for text and then one for colors.
Okay, so then after that question is the one with the equations, and it says that all the colors are combined by the addition of light. And then it has like, the second one down is red plus green equals yellow equals white minus blue.
Right.
So I guess like, why is it white minus blue if it's the addition of light?
I mean, it's still the addition of light. It's just trying to get you to think. So I know that our colors are like red plus green plus blue equals white. I know red plus green equals yellow. Red plus blue equals magenta. And then what am I missing? Blue plus green equals cyan. So if I took white light and I subtracted off, let's say yellow. No, not yellow. Let's say I subtracted off green. Well, white is really a combination of red plus green plus blue. So if I took red plus green plus blue and I subtracted off green, the end result would be red plus blue, which is magenta.
Oh,
They're
got
just
it.
trying to get you to sort of thinking about how am I mixing colored lights? What if I took white light and took off a certain piece of it? What would I be left with? And in a sense, this is pretty much how pigments
Okay,
work.
I feel silly.
No, don't worry about it. We haven't covered it yet. And I mean, this is the first time you've seen it, so. But does that make sense what I just said right there?
Completely, yeah, now I look at it and I'm like, oh yeah.
Woohoo! Light bulb went off.
I get it.
Yay.
Yeah, woo. Cool. Okay. Well, I have more questions, but I'll save them because I think that you're gonna cover them next.
Yeah, I'm gonna cover
Thursday.
the rest of chapter 27 on Thursday.
Cool. Thank you so much.
All right, take care, Allie.
You too.